Let's talk about some different representations of functions. We've already looked at a couple here. One we maybe don't consider as much is a verbal representation of a function. Here's an example. Your altitude as you fly here, altitude, is a function of time. What would a possible description be for the altitude function, and what would a graph look like? So if you think about this, let's actually do the verbal description and the graph at the same time. So we've got time here, and then altitude. So you start at time 0, and you are going to take off. And when you take off, I mean, they pull back on the stick, and that plane really kind of roars upwards. So it takes off and starts going upward pretty quickly. And then as you approach your cruising altitude, it'll level off. So then you got your cruising altitude. And then, you might come in contact with a storm, and maybe they have to increase the altitude a little bit to fly above the storm, and then they level out. And then you decrease your altitude. You're getting ready to come in to the airport, to your destination. And actually, that might be slower decrease here. And then you might get to a certain point, and they say, well, we've got to circle for a while, and so you level off for a while. And then you come in and land. So that might be a possible graph for altitude as a function of time. And you can see that this graph is a function. Any time value down here on the horizontal axis has only one altitude. You're not at two different altitudes at the same time. Another way to look at functions is numerical, so a table. So if you're given a table of x values and f of x values, then you can graph those. You can do what's called a scatter plot here. And I've graphed the values here. So when x is 1, f of x is 8. So I went 1 to the right and 8 up. So that's this point here. 2, 5. So 2 to the right, 5 up. That's this point here, and so on. And we can see that any x value here will not have two y values, right? There's only one y value here above each x value, only one dot. We don't have two dots vertically above each other. So that's a table. So you can give functions tabular. We already looked at graphs of functions. And we did one example looking at algebraic, that is formula. Let's look at another example of algebraic here. So let's say that our function is given by f of x is 1 over root x minus 1. So what is f of 5? Well, that's going to be 1 over root 5 minus 1. So plug in 5 for x. So that's 1 over square root of 4, which is 1/2. What about f at negative 2? So we're going to plug negative 2 in for x. So f over square root negative 2 minus 1. That's 1 over the square root of negative 3. And that is not a real number. So our function is not defined at negative 2. So what that means is that negative 2 is not in the domain of our function f. How about f plug in x plus h? F of x plus h, that's a composition here. So in place of the x here, I'm going to put empty parentheses. So I've got 1 over parentheses minus 1 square root instead of x. And what we're putting in there is x plus h. So there's our function value at x plus h. And then how about our domain? Well, we got a square root there. You can't have a negative under square root. So we need x minus 1 to be greater than or equal to 0. And we also can't have the denominator of this equal to 0. And we need the denominator root x minus 1 is not equal to 0. So, or you might say it this way. We can't have the denominator equal to 0. So, well, let's solve this here. If you add 1 to both sides, this means x has to be greater than or equal 1. And then over here, if you square both sides to get rid of that square root, x minus 1 equals 0. Bring the 1 over as positive, x equal 1. So x has to be greater than or equal to 1, but you can't have x equal 1 because that gives a 0 in the denominator. So if you put these two together, that tells us that we have to have x is strictly greater than 1. So our domain is going to be 1 to infinity and not including 1.